All right, let me move to the second topic, which is single molecule spectroscopy. So here in the single molecule spectroscopy, we're going to use fluorescence correlation spectroscopy. So I'm going to call it FCS. So principle is quite straightforward. So we're going to focus light and as a confocal configuration, and the molecule we're going to diffuse, and once it pass through the confocal volume, then you're going to emit the fluorescent signal. And if the same molecule go on and again, then this fluorescent signal, they're going to have correlation if it is same molecule. So by analyzing these correlation function, then you can determine how many molecules are in the confocal volume using these autocorrelation function. And this is a very powerful technique for the single molecule physics. So if you see this time scale, then you're gonna see diffusion. And if you move, shorter time scale, then you're gonna see triplet state like blinking, and also molecular rotation, and also even anti-bunching. So you can count number of photons using this FCS technique. So the reason why I'm interested in this FCS technique, I encountered this paper. So this is a very interesting paper for the quantum biology. So these paper indicate that, let's say if you have two different fluorophore, and these two individual fluorophore, we're gonna emit photons, right? And they make it closer and closer and closer. And after some threshold, you're gonna see these two fluorophore only emits one photon as a single fluorophore. So this paper, they're gonna mention it work as they're gonna currently behave. So it was very interesting paper for this current energy transfer. So we want to utilize this FCS technique for this kind of purpose. But before that, we want to make another project from this FCS setup because it was very expensive. So we have to make several research papers from that. So the interesting research topic that we found was this miniaturization. So as you can see, this single molecule POCT device, point of care testing device, is very important part and important research theme. So people developed this smartphone-based single molecule sensor or this kind of 3D printed microscope. They will size down these sensors, but still there is very big objective. So unless you minimize this objective, then you cannot make it miniaturized system, right? So our research direction was to replace this objective, large and big objective. The reason why we focus on this area, so as you might know, currently the meta lenses, it can be applied everywhere, even this 2D material spectroscopy and also two-photon microscope as well. So we just thought that, okay, what was our requirements? So to do this single molecule spectroscopy, we need very high numerical aperture and focusing efficiency, and also it work as achromatic lens. So these three are important requirements for the lens design. So yeah, so this is our optical setup. So here we want to replace a big and expensive objective with this metal lens. So here we used this Alexa fluorophore 647. So it was excited by the 635 nanometer laser, and you're gonna emit 670 nanometer, which means our metal lens should work achromatically in these wavelength bands. Okay, so this is our lens we designed and we fabricated, and then here we measured PSF at different wavelengths, 635 and 670, and it was well focused, and also you can see the focus in area match well. And then here we spread the molecule and we measured fluorescence intensity by decreasing the concentration. So up to 10 picomolar concentration, we can detect fluorescence signal. And also, as you can see, once you can this kind of curve, then it might say you're gonna reach the single molecular level. So this autocorrelation curve said our fluorophore, there is only 1.7 molecule in the confocal volume. So this is definitely single molecule sensitivity. And later on, here we prepared another scheme to convince reviewers to the advantages of our meta lenses. So compared to this achromatic objective lenses, so we should use at least 0.5 Na for the single molecule sensitivity, and it is very bulk and also heavy and expensive. So compared to conventional objective, our meta lens, it has similar optical property. We can detect similar brightness of fluorophore, and also we can measure diffusion time of molecule and also confocal volume. And another advantage of this FTS, we can differentiate these 4 different particles, because this fluorophore or quantum dot and nanoparticle, they have different signs, so they have different diffusion time. So by looking at this kind of curve, we can differentiate these 4 different particles. Right, up to here, I introduced spectroscopy technology using Metasurfaces, and let's move to the second topic, which is molecular diagnostic. All right, the research motivation with this molecular diagnostic was to study this quantum enzymology. So enzyme was well known for it can help this chemical reaction by decreasing the chemical energy, reaction energy. But some physicists argue that actually enzyme, it helps this protein tunneling from one side to the another side. So by this proton tunneling, this enzyme can provide a bypass for this chemical reaction. So it can accelerate this chemical reaction. So to see whether it is correct or not, some scientists conducted this kind of research. So they put artifacts, this here metallic nanoparticle, and they thought if proton tunneling takes place, then this metallic nanoparticle will interrupt, so that this enzyme activity will be changed. So to directly see this enzyme activity, they conducted polymerase reaction. Polymerase chain reaction, which is quite well known, golden standard for our COVID testing, right? A very small amount of nucleic acid can be amplified using this polymerase chain reaction. So to check this enzyme activity, you can directly determine the produced amount of nucleic acid. So it turns out that actually this metallic nanoparticle, it can really interrupt this enzyme activity. So if you put this nanoparticle, you will get the less amount of nucleic acid. And after this paper, it was quite interesting. But after this paper, they did similar experiments. So they put enzyme and the PCR mixture on the cavity, and in this cavity and water molecule, they're gonna strong coupled. So you're gonna change the energy of water molecule. So this strong coupling interaction will influence to this enzyme activity as well. So in the resonance frequency, enzyme yield or PCR yield, they change it. So anyway, so to see this quantum enzymology, we also set up this photonic PCR platform. So let me explain this photonic PCR. So for the PCR, experiments, it's very simple. You're gonna heat up the PCR mixture up to 95 degrees C, and then you're gonna cool down it around 65 degrees C, and then you're gonna repeat this process 30 to 40 times. Then after this one cycle, the one DNA can be duplicated. So 1 to 2, 2 to 4, 4 to 8, and so on. So, but by heating up the solution or cooling down solution, it takes time using electrical heating. But here, instead of electrical heating, you can utilize photothermal effect of plasmonic substrate. So this is the very first paper for the photonic PCR. So at the time they prepared gold thin film, and by just turning on and off LED beam, then you can heat it up and cool it down. And by just turn on and off 30 times, you can finish this PCR process. So at the time they just optimized the gold thin film thickness, and then they utilized this blue LED for the photothermal effect. So they can wrap up this 30 some more cycling within 5 minutes. So this is a very rapid molecular diagnostic platform. But it was very interesting, but at the time it was published in this Light Science and Application. So currently this is very prestigious journal, but at the time it was not that high. But this photonic PCR technology, it got attention again during this COVID period. So there are a lot of photonic PCR platform. So from this very first gold thin film, people developed this kind of 3D plasma structure to broaden the absorption peak. This is gold film absorption peak, but this 3D plasmonic structure, it has broadened absorption peak. So instead of using this blue LED, they can utilize white LED. So it has a cost effectiveness. So also you can finish the 30 thermal cycling within 3 minutes and 30 seconds. So this is the device they developed. And except this nanostructure, these functional nanoparticles can do similar function, but nanoparticle, they have small surface area, so it needs very high power diode laser. So as you can see here, diode laser is used to heat it up, but for the cost was not that effective, right? And also they use very high power LED or laser and so on. So our motivation was to optimize the nanostructure and to maximize the photothermal effect. So we just designed a perfect light absorber, and then we just thought that okay, we can make it better. So simply we make this ring-shaped nanostructure. We fabricate it on 6-inch wafer using colloidal lithography. So design principle is quite straightforward. Here we're gonna make this impedance matching, and then compared to the gold film, our titanium nitride absorber, it has broadband absorption from 400 to 1000 nanometer. Yeah, as I mentioned, here we utilized colloidal lithography. So we just use two-step etching process by this polystyrene bead. And then we can make it on 6-inch wafer, this very precise nano ring. Yeah, and then we're gonna heat it up, the PCR mixture using IR LED. So compared to the gold film, our metal absorber, it has superior photothermal effect. So if you don't put any PDMS well, then we can finish this 30 thermocycling within 3 minutes and 15 seconds. And if you put this PDMS well to put PCR mixture, then it's gonna extend it a little bit. But anyway, you can finish within 7 minutes. You can here. This is the example before PCR and after PCR. You can see this amplified nucleic acid. And also, this is our device. And also every thermocycling, we can monitor fluorescence signal in real time. And also, we detected the SARS-CoV-2 Omicron RNA as well. So, yeah, this is the photonic PCR platform using Metasurfaces. And let me conclude my talk by introducing this final theme of multifunctional bioimaging. I think all of you are familiar with the advantages of metal lens. So I think the biggest advantage of metal lens is multifunctionality. In a single device, you can make a chromatic aberration or tunability and so on. So you can see this achromatic metal lens now is available in daily life. So it can be applied for AR VR display as well. And the biggest hurdle for this metal lens for practical application was this nanofabrication or nano manufacturing method. But utilizing this nano printing technology and also DUV photolithography, now we can mass manufacture these metal lens. And also another big hurdle was this active modulation. So people utilize this just simply stretching and releasing PDM and substrate, and they can a little bit tune these focal points, but it was not that accurate. And also, some people used this phase change material like GST, but still there were not there. They don't have a perfect solution for visual frequency. So when I was PhD student in postdoc, I found this concept. I just simply merge these metasurface and liquid crystal cell to actively change the focal point. So our principle was quite straightforward. Here we design spin multiplexed varifocal metal line. Actually, not varifocal. This is bifocal. LCP and RCP light have different focal points, like this. LCP will be focused here. RCP will be focused here. And here, by integrating liquid crystal cell, then we can change the input beam pollution state. So by electric bias, we can change these focal points. Let me show you the video. So if you're looking at a single focal plane, then it can be focused or defocused. And if you put different image target at different planes, then you can see these two different objects. So this is kind of zoom function, right? So this is electrical tunable varifocal metal lanes. And I think that we can utilize this concept for another imaging operation. For instance, this kind of edge detection. So this edge detection is quite well known imaging technology for object recognition.